Atoms. They are almost indescribably small. Their radii are measured in picometers. 1 picometer is equivalent to a trillionth of a meter. Let's put that in perspective. On this ruler here, 1 centimeter would be equivalent to 10 billion picometers. That's how small atoms get. And yet atoms are mainly made up of nothing at all. If this ball represented the proton at the center of a hydrogen atom, the single electron orbiting around it would occupy a spherical orbital 8 kilometers wide. So most of the atom is literally nothing. Since atoms are so unfathomably small, the subatomic particles that make them up, the protons, neutrons, and electrons, must be even smaller still. Rather than try and wrap our brains around these tiny numbers for the masses and charges of these subatomic particles, we mercifully decide to use a simplified system of relative masses and relative charges. The relative masses relate the masses of atoms of elements against each other, using 1/12 the mass of an atom of carbon-12 as the universal yardstick. This effectively gave protons and neutrons a mass of 1 atomic mass unit. Electrons are so much smaller than protons and neutrons, they effectively have no mass, and therefore their mass is seen as negligible when considering the mass of an entire atom. Also, since all atoms of elements are electronically neutral, if protons are given the relative charge 1 positive, neutrons are uncharged, and electrons are given the relative charge 1 negative, by definition, atoms of all elements will have equal numbers of protons and electrons for them to have no overall charge. So, to build simple representations of atoms, all we need to know is 2 numbers. Its mass number, the top number, which counts the number of protons and neutrons found in the nucleus, and the bottom number, the atomic number, which just counts the number of protons in the nucleus. The number of electrons will be equal to the atomic number or the proton number, since atoms are electronically neutral, but they don't affect the mass of the atom as they have virtually no mass. So the mass number only really represents the number of protons and neutrons together. Some basic arithmetic gives us the number of neutrons. The mass number minus the atomic number is equal to the number of neutrons. Let's build an atom of helium. Helium has the atomic number 2, and therefore 2 protons in its nucleus. Its mass number, the number of protons and neutrons, is 4. So if we take away the atomic number, 2, from the mass number 4, we're left with 2 neutrons in the nucleus. Place these between the positive protons to create some space, as protons will naturally want to repel each other as they have like charges, and that will make our nucleus unstable. So we always want to try and keep our protons apart by placing neutrons in between them. Finally, add the electrons onto the energy level known as a shell. The first shell has a maximum capacity of 2 electrons, and helium only has 2 electrons. So that's 1 and 2. Great, all done. Next, let's build a fluorine atom. Atomic number 9 means 9 protons in the nucleus. Its mass number is 19. So, mass number minus atomic number, 19 minus 9 equals 10 neutrons in the nucleus. Atoms of elements are electronically neutral, so there must be 9 negative electrons to cancel and balance the charge of 9 positive protons. Now, 2 electrons can fit in the first energy level or shell, but that's it full. So the other 7 electrons we need to place have to go in the higher energy second shell. That has a maximum capacity of up to 8 electrons. And hey presto, a fluorine atom representation. Lastly, let's have a go at an aluminium atom. Atomic number 13 means 13 protons in the nucleus. The mass number is 27. So mass number minus atomic number, 27 minus 13, means there are 14 neutrons in the nucleus of an aluminium atom. Now, disclaimer, I'm not going to be able to keep the protons separate in this diagram when I cram all my neutrons in there, but believe me, the number is the key thing, and that will be right. There'll be 14 in that nucleus. Since the atomic number is 13, there should also be 13 electrons surrounding the nucleus in the energy levels known as shells. Now, the maximum capacity of the first energy level or shell is 2 electrons. The second shell is higher in energy but has a maximum capacity of 8 electrons. So we are forced to go out to the third shell to place aluminium's final 3 electrons. That's 1 and 2 and finally 3. And that is a representation of an aluminium atom. The pattern for electron configuration at GCSE is 2 in the first shell, 8 in the second shell, 8 in the third shell, and then 2 in the final shell, and we stop at calcium, element 20. It does go beyond that, but at GCSE, that is the point at which we stop. So folks, there it is, atomic structures using a sweet shop favourite, Jelly Tots. If you like the video, then please don't think about giving it a thumbs up, and maybe even consider subscribing for updates of our future content. Oh, and if you were wondering what electrons taste like, they're kind of lemony. Take care, guys. Bye now.